All right, hello class. Mr. Bean here. I'm with B4 cohort 1, and we're going to be doing kind of discussion on Lab 41 on how to do it and stuff. Okay, so for those kids who miss class, or for those kids who are in class but aren't paying attention, falling asleep, or didn't understand what I'm doing. Okay, you can always refer back to this video for future review. All right, so up here we have what's called centripetal, which indicates center seeking. Okay, center seeking. Okay, and so here we have a nice circle up here. Normally, I would draw this up on the board, but in fact, let me go ahead and try that real quick here. Let me hit pause. All right. So centripetal means center seeking. Okay. So what happens is that let's assume that we have some object right here, and we're going to use black here, and it has maybe some mass m. Okay. So in this case, it was the bob on the end of the string. It could be a car or anything. Just it has some mass, and we'll say that it's going to go in this direction here. Okay. Okay. Kind of like this right here, right? Okay. All right. So we know that this is the radius here, right? Okay. Now, at some time delta t, right? Uh, we have the object is now here, right? It's moving in a circle. Okay, and we can also draw a line, kind of dash line, like right here to here, and this is also the radius as well. Right, everyone's good. So it moved. So sometime delta t, it moved to a new location. Okay, and right here we'll go ahead and call this delta theta because it did move some degrees. Okay, it moves a little bit right here. Okay, so delta theta. Okay, all right. Okay, and okay, so here now, if it goes all the way around, okay, if it goes all the way around, what is that called? This distance here, was that or circumference, right? Yeah. So the distance or the circumference, if this object goes all the way around, it goes back to the starting point right here. This would be 2 pi r. Okay. That's the distance traveled, 2 pi r. Now, for this class, if you want to, 2 times pi, you can just say 6.28, okay, just to help with simplified calculations, okay, 6.28. Okay, now, the time it takes to go all the way around is called the period, okay? So we'll say time for we'll say one cycle, okay? Uh, uh, One cycle, one rotation, one revolution, one oscillation, one vibration, anything there, it would be the period. Okay, time to complete one oscillation. Okay, and the units here will be seconds. So we'll go ahead and use the units of seconds here. Okay, all right, let me hit pause again real quick. All right, it's now, period is the time for one cycle. And usually you have capital T that we use for period. I don't know why we use capital T because last unit we used it for tension. So you have to kind of be versatile. It could be tension or it could be period. So you have to kind of be careful here. Frequency. Anybody know what frequency is? Okay. Any computer geeks in here? Kind of. Okay. No, none. Okay. I am. Okay. So I have for Christmas I have an 8-core processor, each at 1.33 gigahertz. Okay, so that means gigahertz. Okay, that means 1.33 billion calculations a second. So cycles per second, some revolutions per second, rotations per second, anything per second is frequency. Okay, so frequency is quite honestly is just 1 over the period. So if I know the period, I take 1 over the period, I get frequency. Okay, and so what happens now is that for unit wise, okay, for units here, it's really 1 over seconds. Okay, it's 1 over seconds. Okay, so if I have 1 over seconds, that's really hertz. So 1 over seconds has a special designation called hertz. And here's where the radians come in. Since it's 1 over second, I can put, so 1 over second here, I can do cycles per second. That's the SI unit. I can do revolutions per second, radians per second, So anything per second is frequency, as hertz. Okay, so that's something that we'll need to be aware of. Okay, so now speed. Okay, so if I want to know how fast this is going around, the speed here, how fast it is. So the speed here will be taking the velocity vector, putting in an absolute value. That means the magnitude, which is speed, is simply, we know it as distance divided by with a period, right? Or distance divided by t, or the period. So in this case here, the distance will be 2 pi r divided by t. Okay, so this is how you would find the speed of an object going in a circle. It's 2 pi r divided by the period, or the time. So 2 pi r, that's for one revolution divided by the period. Okay, and that gives you the speed. Okay, it's how fast it's going, not necessarily vectors. Okay, all right. Now, continuing on with this, we'll use this circle over here now. Okay, let's take a look at, so we understand what radians are, right? You take the radius and you kind of string it along here. That's one radius. There's 2 radians, pi radians, and all the way around is 2 pi radians. Okay. Now, ever heard a term called arc length? Sound familiar? Okay. All right. You may have heard about it. Okay. So, all right. We'll go over here. And I'm going to go ahead and put a bob here again. And again, it's going to go in this direction here, like so. Okay. So again, at some time, delta t, right, is going to be at this location here. Okay, it's moving in a circle. Okay, and from here, I can also draw a line here, and there's the radius again. Okay, that doesn't change. And of course, this here is delta theta. Okay, now we only went a little bit. Okay, so question is, what is this distance right here? Okay, what is this arc here, this arc length here? Okay, this is called the arc length. And we'll go ahead and use the symbol S for arc length. Okay, now the arc length, if you may have forgotten, is simply R times delta theta. But here's the caveat. This has to be in radians. Okay. Okay. That has to be in radians. Okay. So S is arc length, and it is simply R times delta theta. Okay. All right. Okay. All right. That's arc length. Okay. All right. Now, angular velocity. Okay. A new term here. Now, not regular velocity, angular velocity. We're going to be using a symbol called omega. It looks like a little W here. That's omega. Okay. So omega is simply delta t. Okay, so first of all, so we have here delta, so omega is going to be delta t, right? So here we have your delta, okay, hold on here, hold on. Let me backtrack real quick here. Okay, all right, let's go back to here. So angular velocity is omega. Okay, we'll come back to this, come back to this in a second. So here is velocity, v. Okay, so how can we connect velocity, arc length, and angular velocity all together? Okay, well, here's how we would do it. So velocity is simply, was it distance, right, over time, or delta t in this case, delta t. Okay, all right. Now the distance which this travels is nothing more than the arc length, which is s over delta t. Okay, all right. We'll put here delta t. Okay, all right. So what is s? S is simply r times delta theta over delta t. Okay, like so. All right. All right. So now take a look here. Take a look at this part right here. So if I have delta theta over delta t, the rate at which theta is changing with respect to time, that's called angular velocity or angular speed, which is omega. So this ends up being r times omega. Okay, so velocity also equals, so tangential velocity also equals r times omega. Okay, and omega is the rate at which speed changes, or theta changes. Let me hit pause real quick. So if you need to, sometimes tangential velocity, you could write it like this, where this is omega and this is r. This is very similar in math class to y is equal to mx. Okay, okay, where m is the slope, omega is like the slope. It doesn't change. It's the same. What affects the tangential velocity or tangential speed or velocity is the radius. Okay, all right. Does that kind of help out a little bit? Kind of okay. So we'll be doing some things here. Okay, now last one here, as far as this page is concerned. Okay, so now there's an equation here for acceleration. Okay, okay, it's centripetal acceleration. Okay, so centripetal acceleration, we'll put a little c here. Okay, uh, the magnitude. So we have speed now. Acceleration. Okay, the equation is just going to be v squared over r. Okay, okay, okay. That's the centripetal acceleration. Okay, it is v squared over r. Okay, now, however, okay, now there's different manifestations of this. Okay, so velocity, remember, was a 2 pi r, right, over t. Okay, so remember this right here. So if I was to take v squared, I would now have 4 pi squared r squared all over t squared, like so. Okay, so if I substitute this into here, okay, does one of the r's cancel out? Okay, so good. So centripetal acceleration now, if I make that substitution, is okay. You can also express it as 4 pi squared r divided by t squared. Okay, so this is if you have period and radius and you want to figure out what the centripetal acceleration is. Okay, you could do it by this. Now, where this equation comes from is beyond the scope of this class. Okay, so but suffice to say that's the equation that we'll be using. In AP, we actually talk about how to do that. It's more heroic algebra and heroic geometry, which we don't want to do right now. That's too much. Okay, however, now remember centripetal means center seeking, right? Center seeking. So we need to show how is it center seeking. Okay, so again here, we'll go ahead and kind of draw this right here real quick. Here's our radius, right? And here's our mass right here. Okay, so at this location, okay, we have a velocity vector, tangential velocity vector that looks like this. Okay, and we'll call this here VO. Okay, okay, everyone's good right there? That's VO. Okay, at that moment of time, that's the tangential velocity vector at that moment of time. Okay. Now, at some time t, it might be like right here, right? Is that a new location? Okay. Here's our right. Okay. I want to go ahead and change to I'll change blue. So at this location, there's a new tangential velocity vector that looks kind of like that. Okay. And this will be the final velocity. Okay. Okay, so everyone's kind of good. So it moved some time, and at that location, I draw another velocity vector which is tangential to that. Okay, so everyone's kind of we're good so far. Okay, all right, okay, and okay now, remember now. Let's go back to black here. Normally speaking, acceleration, right? Okay, acceleration is usually v minus vo divided by delta t, right? Okay, all right. So these are vectors. These are vectors. Okay, we have two vectors here. Now, I can also say that acceleration is also equal to v plus minus vo, right? Okay, all right, okay, all right. And delta t is a scalar, so it's not really involved here. So is this okay? Everybody feel comfortable? We can do that? Plus the opposite? Okay. All right, so here's VO. Okay. So would negative VO be like this? Okay. Would this be negative VO? Yeah, negative VO is just the opposite direction, right? So when we add vectors, do we go head to tail method? So here is vector V, here is VO. I'm going to take the head of this and add it to the tail of this. So if I do that, if I go up here, I'm going to slide this over to here. when I do that, I get a vector that looks kind of like this right here, right? Okay. So this is minus VO. Okay. Now the resultant vector. Okay, we're going to connect the dots now. So let me go over here and I'm going to go ahead and use red. Okay. So if I have V and I'm going to add it to minus VO, here's the velocity vector like this here. That's the resultant vector, delta V. Okay. And which direction is that arrow pointing? Toward the center? Yeah, so center seeking. Okay. So this is the non-calculus version. Okay. So it's center seeking. Okay. Yeah, usually we have the chain rule and do some substitute. We have sine and cos. Yeah, this is much easier. Okay, okay, all right. So this shows us that the acceleration is center seeking. Okay, all right. Everyone's good. Okay, all right. Okay, all right. Okay, so the next step would be centripetal force. If the centripetal acceleration is center seeking, which direction is the centripetal force? It's also center seeking too as well. Okay, good. So centripetal force could be tension, it could be friction, or it could be gravitational. Okay, all right. Example one: the car turning. Okay, all right. So a car turning. So usually there's a highway that looks. Here's a two-lane highway here. Okay, and here's the other highway here, and we have a car. We have a car here, and the car is moving in this direction here. So here's a car moving, and there's usually some coefficient of friction between the tires and the asphalt. Okay, so ever wonder why engineers use tires and asphalt and concrete for roads? Because the friction is greater, right? Okay, and you can reduce the friction by adding ice or making it slick or oil. Okay, so most highways, I think they have it set for there's a 10 miles an hour fudge factor. So if it says 55, don't quote. Okay, I'm being recorded, so I better not say it. Okay, you should go 55, but there is a slight fudge factor. Okay, but you also okay. So they take this all into consideration: the mass of the car, tires, and road surface for coefficient of friction, and they actually have to design the curve so a car can go 55, 35, 45 based on these measurements here. Okay, so if you're going to be a civil engineer, this is the kind of stuff you would do. Okay, so here there's an actual radius here. Okay, and we'll call this the radius r because this is a circle, right? Okay, probably like right here. Here's the radius here, and it's a circle. So you have mu here, right? Okay, so centripetal force is going to cause the car to go in a circle. Okay, so let me go and change here. So what we have here then from Newton's second law, we have sum of the forces has to equal m a c, and c stands for centripetal acceleration. Okay, now in this case, what is the force that's causing the circular motion? Friction, absolutely. So we'll say here, this is going to be the force of friction, which is going to equal MAC. Okay, so force of friction. Now we know it to be mu, right, times the normal force, right, is equal to MA, like so. Okay, all right. So here's mu. Now Fn is nothing more than mg, right, is equal to m. Now remember, centripetal acceleration is really v squared over r, right? Okay. So from here, did the m's cancel out? M's cancel out. So I have here mu g is equal to v squared over r. So we'll go ahead and stop here. So from here, we can solve a lot of questions, a lot of problems based on information given and so on and so forth. Okay. So they may ask you for a certain coefficient of friction, what's the maximum speed a car can go before slipping? So that's how they figure out. So they ask you on a curve, how fast can you go? So if I know the coefficient of friction and I know the radius, I can calculate the speed, the safest speed. So if I go beyond this speed, I might slip or I might go off the road. Okay, so this is kind of how they do that. Okay, now remember that v also equals what, 2 pi r over t. If necessary, we may have to do a substitution. But this is how you would solve the first simulation. Talks about cars. Okay. All right. Now, next one here, we have the vertical string problem. So let me go ahead and hit stop here real quick. And so here's our problem here. So we'll go ahead and have like a string here, and we'll have the ball right here, or the mass here. Here's our string right here. Okay, so this is radius here, right? So let's imagine the top. Okay, this is top. So let's take a look at the top here. What are all the forces acting on this ball right here at the top? Okay, so we have what tension, right? Tension going this way. And is there all, well, here, I should put, well, because I don't want to confuse this with period. Let me go ahead. Let me erase this here. Okay, so let's do uh, F with a T here for tension. Okay, yeah, force of tension, and also what, mg. Okay, so we have tension and mg all acting in this direction. Okay, now since both of these are acting this direction, which way is the acceleration vector going to? It's also going down as well, right? So acceleration, force of tension, mg are all acting downwards. Since all three are now, normally speaking, whichever direction the acceleration is, you want to call that positive. Okay. So in this case, are all three going down? Okay. So we'll call that direction positive. So going down is going to be positive, going down, right? Okay. Going down. Okay. So we have here sum of the forces, right, is equal to, so we have here sum of the forces here is equal to, we have here, this is going to be M AC here, right? MAC, okay. All right, so we're here, okay. So some of the forces we have here, we have a force of tension plus mg, right, equals MAC, okay. So the force of tension is going to be MAC, right, minus mg, okay. So we have a subtractive effect there, subtractive effect, okay. All right, everyone's good so far? We're good, okay. Now at the bottom, we'll use a different colored pen here. We'll use maybe green, okay. So at the bottom here, okay, here's the ball here at the bottom down here. Okay, we want to examine all the forces acting here. So down here, so we'll assume the ball is here. Which way is gravity going? Yeah. So mg is this way, right? And which way is tension? Up, yeah. So force of tension is this direction. Now here's the important part. Which way is the acceleration vector going? Up, center seeking. Always goes toward the center, right? So the centripetal acceleration vector is also going this up in that direction too. That's the key. So which way is the acceleration vector going? It's going up. So that we'll make that positive. So in this case, we'll call going up positive. Okay, everyone's good so far? We're good? Okay. All right, so some of the forces. Uh, okay. Jeez. Okay. 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 So some of the forces is equal to, here's M uh, AC, right? Centripetal force. Okay. So some of the forces, so going up is positive. So there's force of tension right here, right? Good. And mg is subtractive, right? Equals MAC. Now, Karen, here's where math and physical reality intersect. The force of tension now is going to be MAC plus mg. Ah, okay. This is beautiful here. This is where mathematics intersects physical reality. Okay, that's why it's heavier, because there's greater tension. Okay, now question was what? Okay, now question might come up. What's the minimum speed required for this to happen? Okay, what's the minimum speed? Okay, so let me go ahead and kind of go like right here with let me do black here real quick. So question is, so up here, what's what's V minimum? Okay, What's the slowest you can go in order to negotiate the circle? Okay. So now, when this happens, okay, remember now, when the ball drops, what's happening to the tension? Is it zero? So at the very top, if tension is zero, what's going to happen to the ball? It's going to fall. So, so when we look at this, okay, so what's V? What's V minimum? We have to look. We'll say look here. Look when the force tension is equal to zero. When the tension is zero, what happens? So we'll go up here. So this is tension right here, right? That's zero, right? Okay. Now here's M. I'm going to fact here's M. Now AC, isn't AC just V squared over R? Okay. Minus mg. Okay. All right. So we have, okay, we're everybody good so far? Okay, now take a look here. So AC is really V squared over R. What cancels out right away? Masses cancel out, right? Okay. So now I want to solve for V, right? So if I'm using my advanced algebra skills here, right? So I'm gonna bring G over to the other side. So here I have G is equal to V squared, right, over R. So to solve for V then, V is going to be the square root of G times R. So this is how you calculate the minimum speed required to negotiate that circle. Okay, because tension has to be zero. Okay, so does it equal that or should it be greater than that? It should be greater than that. Because if I go there, it's going to fall. So it has to be greater than that. That's the minimum speed required. Okay, all right. Now, the next part here, okay, let me hit pause here real quick. Okay, class, to finish off here, if we had a bucket of water, so let's suppose we had a bucket up here. There's a bucket here, and there's a bucket at this location right here. So here's a bucket here, and let me make a better bucket here. Okay, let's make a better bucket here. So here's a bucket here. And there's some water. We'll use blue for water. So there's water in here, right? There's water. There's water. There's water, and we'll color in water here. Okay, and let's say it's going in this direction like this. It's going in this direction. Okay. All right. So, question is, what's V minimum? What's V minimum so no water comes out? See, what's V minimum? All right. So we'll go about right here. We'll go to right here, and let's say that this is R here. Radius is R. Okay, and it's going in this circle here. What's the minimum speed in order for this to go all the way around? Well, so you have inertia acting here. You also have the normal force here acting on the bottom of the bucket here. So we'll go ahead and take a little piece of the bottom of the bucket, and let's examine all the forces acting on this. Okay, you do have mg acting this way, force of gravity, and also you also have the normal force acting in this direction as well. Okay, and the centripetal acceleration vector is also acting toward the center. So all three are acting downwards. Okay, all three. So if I go over here and I go sum of the forces, right, is equal to MAC. Okay, the force in this case is going to be the normal force. There's the normal force here, and we'll have here plus mg, right, is equal to m, and centripetal acceleration formula is v squared over r. Okay, so in order to do this problem here, we have to figure out, we have to look at the situation where the normal force is equal to zero. Okay, so when that's equal to zero, we'll put a zero in here. There's plus, this is now mg is equal to mv squared over r. So looking closely here, we see the masses cancel out. That's interesting. Okay, so now we have g is equal to v squared over r. So in order to do this here, we have v squared is equal to gr. Therefore, the minimum speed v has to be greater than the square root of gr. So if you want to, you could say that v must be greater than the square root of gr in order for in order for the bucket no water to escape. So really, it's dependent upon the radius. So the radius, the square root of the radius determines the speed to go all the way around. All right, this will conclude this discussion on Lab 41, Circular Motion SIMS.